Okay, so this is problem 2 from the 1992 Physics C Mechanics exam. So the problem asks several questions about the rotational motion of a system which consists of a massless rod on either end of which there are spheres that weigh mass m, and a bug comes and lands on top of the left sphere, and the mass of the bug is 3m. The axis of rotation is through the center of the rod, and the length of the rod is 2L. So counterclockwise is positive and clockwise is negative in this case. So part A asks for the net torque on the system. On the left side we have 3 mgl as the gravitational torque for the ladybug, mgl for the left sphere, and on the right side we have mgl for the right sphere, which is subtracting because that direction is negative. So net torque is just 3 mgl because the system was in equilibrium before, so that's also just intuitive. Part B asks for the angular acceleration. So first I found the moment of inertia of the system. So this equation right here, 4ml squared, is just the moment of inertia of the left sphere plus the moment of inertia of the ladybug, both of which are just considered point masses in this problem. So that's 3ml squared for the ladybug and ml squared for the left sphere. And obviously, since they're point masses, it's just mr squared is the moment of inertia, and r in this case is just L. And then we have the right sphere, which is just ml squared again. So the total inertia is 5ml squared. Summation of torque equals I alpha. So alpha equals summation of torque over I. 3 mgl over 5 ml squared equals 3g over 5l as the angular acceleration. Part C asks, okay, so in part C, the system is vertical, as in the bug has rotated and it's now towards the bottom. Like the left sphere is at the bottom and the right sphere is at the top, and the rod is vertical. So it's asking, well, it wants to know what the angular velocity of the bug will be at this point. So I used a kinetic rotational energy conservation equation. So, well, first, there's no kinetic rotational energy initially, but there is a potential energy. And then after that, there is a rotational kinetic energy, which is just 1/2 I omega squared, and then there's the potential energy. So you get 3 mgl, so 5 mgl minus 2 mgl, 3 mgl equals 1/2. You substitute in I, which is 5 ml squared. So 3 mgl equals 1/2 times 5 ml squared times omega squared. And by rearranging that, you get omega equals the square root of 6g over ml. And then part D is asking for the angular momentum of the bug at that point. So that's simple. That's just the moment of inertia times angular velocity, which equals 5 ml squared, which is I, times the square root of 6g over ml. Okay. The last part asks for the force of the sphere on the bug when the rod system is vertical, so that the bug does not fly off the sphere. Remember, the bug is basically upside down, holding on for dear life at this point. It's a vertical system, so the sphere needs to keep a force. There needs to be a force between the sphere and the bug so that the bug doesn't just fly off. Alright, well, first we need to know that there's actually a summation that's happening here. The summation is that the centripetal force on the bug actually equals the contact force between the sphere and the bug minus gravity. So that contact force is opposing gravity, which is pulling the bug down and ordinarily would make it fly off. So first, centripetal force equals mv squared over r. V just equals r omega. So when you substitute r omega into the FC equation, you get m r squared omega squared over r, which cancels to m r omega squared right here. And then you substitute in again. M of the bug is 3m, r equals L, and Omega, as we found before, was the square root of 6g over 5L, so squaring it gives you 6g over 5L. And that, when you simplify, is 18 mg over 5. And again, this is a summation, so 18 mg over 5 is equal to the force of the sphere on the bug minus the weight of the bug. So the force of the sphere on the bug equals 3 mg plus 18 over 5 mg, which just comes out to 33 over 5 mg, or 6.6 mg. That's the contact force between the sphere and the bug.